Our next speaker is also working in Skoltech, where he heads the science group, which is called Advanced Data Analytics in Science and Engineering. He is the head researcher of AIRI, the Artificial Intelligence Institute. Evgeny Burnaev. He specializes in applications in industrial analytics and developing the ML methods. He is going to talk about the generation of attacks and the protection from these attacks. Colleagues, hello. Today I'm going to talk about the robustness of neural networks from the geometrical sense of the word. Let's talk about adversarial attacks in case when the data are based on the diversity. The standard adversarial attack is when we have an image and we add a very small thing to adversarial thing to the image that we won't see with an eye, but it changes the result. One pixel attack. You just change one pixel and the classifier does not classify the image properly. But we understand that with these approaches there is no connection with the components of the objects, and meaning the pixels of the image. How can you account for that? The standard way to account for that is the manifold nature. The manifold nature, the diversity, can be thought by this, can be explained by this formula. This is the manifold based on the map. X is our image, Z is the vector, and the other one is a non-linear image. Let's look at this manifold. The black are the real-world images. For instance, the dog, an image of a dog, or an image of another dog, or an image of a cat. And for instance, we try to resolve a classifier task. We try to divide dogs and distinguish dogs between dogs and cats. But there are different objects there. There is an image of a muffin that looks like an image of a dog, and this image is near the boundary of the classifier. That might lead to the fact that the neural network might give the wrong classifier after that. Based on this basic idea, we can talk about the possibility of implementation of adversarial attack based on the diversity of the data. First of all, you need to be able to generate data based on the diversity, on the manifold. For that, you need generative models. There is a space with a simple distribution, let's say Gaussian one. We generate a number of latent vectors. So we built a convolutional network in a special way that displays the vectors from the pictures of the real world, or it gives a description of some difficult objects. And this model basically makes an induction for the distribution. This distribution is pretty simple. It is proportionate to the multiplication of the prior distribution. So we made this model. How can you generate the pictures? For instance, L on x-axis is a dissimilarity measure to compare objects. X is attacked object and Y is label of the attacked object, is real branch. So to generate the object that is not only similar to the real one, but is similar to the one that is being under attack, you need the generative distribution that should be multiplied by a multiplier that is growing if the similarity similarities going down between the object and the attacked object. And now let's talk about the fact how can you generate the object that will not only look like similar like the one that we have delivered, but how can we make a mistake? SX is the attacked classifier, but it is not available to us. But there is a sample based on which it was trained. You can get a sample of data that might imitate the selection of data, this data sample that is usually used. Let's say this S is a surrogate classifier. We need that to understand what mark are we going to have for the object that we're going to generate. So to generate the description of the object that is on the one hand based on the diversity, so it looks like a real picture. On the other hand, it's not really different from the description of the attacked object. At the same time, the neural network is likely to make a mistake based on that. You need to multiply the generative model on the multiple that is very different from the subject, and multiply by the multiplier if there is a difference between the marks in the objects.
This way, using this distribution, you can generate new descriptions of objects which, with high probability, will be similar to the attacked ones, but the neural network will likely to make a mistake with them. At the KDD this year, my colleagues and I, we used this methodology for classification using transactional data. Let's say we have transactional data sampling. Using the sampling, the bank can assess the creditworthiness of a borrower. So this is a kind of a mock model of the transaction, and the bank declares the customer non-trustworthy, non-creditworthy. We assume that there is a sampling of transactions which is similar to the one used in building the initial model. So we use it to build a surrogate model and also an adversarial attack approach. After that, this adversarial mechanism can supplement the user's transactional history in a way that doesn't really change it dramatically, so it stays pretty much the same. But still, this transactional history leads to a situation where, with high probability, the classifier, the actual model, will declare the user creditworthy. This approach is difficult to implement in practice for organizational purposes, but this adversarial attack methodology is very useful because this way you can generate outliers to test the robustness of models in critical applications. So we have talked about adversarial attacks that can be generated based on the manifold of data. And now let's talk about how you can resist these attacks, also given the manifold of data. This work was also prepared for the MLP conference this year. Once again, let's talk about the topological data analysis. This slide shows a donut and a coffee mug next to it. Topologically speaking, if the donut was made of rubber, then with some sort of continuous transformation, it could be transformed into a cup of coffee, a coffee cup. So topologically speaking, these two objects are similar. But if we increase the scale of the donut with a piece of it bitten off, then with this scale, the two objects will be very dissimilar. So topological analysis is some kind of machinery which helps you assess the scales at which significant structural properties of objects change their form. What does it look like in practice? Let's say we have a cloud of dots in a 2D ring with a hole in the middle. We start building a sphere, changing the radius of each dot from 0 to plus eternity, plus infinite. At some point, the spheres start to intersect, to touch each other and then intersect. on the right side of the graph, we are showing the so-called persistence diagram. What is that? Each dot on this diagram means that its x-coordinate is the least value of the radius, with which the spheres are touching each other in a way that there is a cycle which basically covers the whole. The y-coordinates of the dot is the maximal value of the radius, after which the sphere is so big in radius that this hole disappears. On this persistent diagram, in addition to the cluster of dots close to zero, there is one dot that is very far away from them. What is this dot? This is the maximal hole in the manifold of this data. So this is the peculiarity that is sustainable in this data. You can use a similar approach to multidimensional data as well, reviewing holes of various dimensions, 1D, 2D, multidimensional. As a result, what we get is a persistence diagram which can characterize complex local structural attributes of a multidimensional manifold of data. Using this diagram, you can calculate various characteristics. Let's call them topological characteristics. And now how you can use this tool in order to analyze sequences of symbols or texts. I will primarily be talking about the text example, but just a side note, you can use it for other sequences, for example, a sequence of transactions. On the left, you see a standard model of the transformer, a standard transformer model. This commodity model is pretty much the basis for most NLP models. It helps you create an attention map. An attention map means that some words in the sentence are very closely related, and so the value, the number on the attention map characterizes this relatedness, and then there are some words that are not really related to each other. This can be described as a matrix or as a graph, as a bipartite graph. Then there are weights that characterize the relatedness of words in a sentence. With this graph, you can use it the same way as a cloud of dots. Each graph node is like a dot, and the edges are the distance between the dots. And we can also determine the threshold. It will be analogous to scale, from 0 to plus infinity. This way we are basically getting rid of the edges with small weights. This way we are basically doing filtration, a sequence of bipartite graphs with which we can also calculate the sequence of cycles. And based on that, we can assess the persistent homology. And now our problem. The problem is resisting adversarial attacks. Basically, we want to build a classifier which, for a certain sequence, will tell us if it's artificial or not. We have texts from the web, we have user comments, and then we have some texts from news bulletins. These texts, some of these texts are real, some of them are artificial, generated by a generative model. We assessed their attributes, their persistent diagrams, and based on that, we calculated different statistics. For example, the average life of a cycle, or the dispersion of the cycle. As a result, you get a number of attributes. You can see on the slide what you can deduce from these results. If we use the standard, the commodity BERT model, and train the last linear layer that's responsible for classification, then the accuracy is way less than the accuracy of using standard logistic regression, which uses topological attributes. After we discard the non-relevant ones, we are left with roughly 1,000 attributes, which means that topological attributes contain truly valuable information for understanding structural properties and understanding the scales in which certain relations within a text occur. So this increases the accuracy of classification. Of course, we can do the fine-tuning of BERT for this kind of data specifically, but millions of parameters, it takes a lot of time and the result is not guaranteed. So we have learned to classify data as real or artificial. Well, we have a manifold of data. Can we compare the manifolds? Let's talk about this. The main idea behind this problem is that at the moment generative adversarial models are used everywhere, but there are no good ways to assess the quality of these models. We have real images, we have artificial generated images. Yes, we can use the standard threshold distance, but what if it's not about images, something else? Let's say we are comparing topological attributes of manifolds, of real data and artificial data. This idea was very timely used in the work done by my colleagues. The only project of that kind at the time where an effective metric was built to compare guns in how well they imitate this distribution. We calculate the topological attributes for real and artificial manifold data, and we do the comparative analysis with the geometry score. But this approach needs to be developed further, because when we compare the manifolds, we are not taking into consideration the positioning of those manifolds with regard to each other. In our recent publication in NeurIPS, we suggested the following. Let's say we have a manifold of dots that are real and then another one that is artificial. Let's assess the topological attributes of the so-called vector space. What does that mean? We are combining the manifolds of dots and we deduce the second manifold from the combination, but in a very peculiar way. Some of the dots from the second manifold are close to the dots from the first manifold, and if they are close to each other, we merge them and we leave the space vector, and then we calculate the topological attributes. What does it look like in practice? We have the red dots, the red manifold P, and the blue manifold Q. We start with some value of scale, with some value of radius, and we start combining these dots. First, we deal with the red ones, then with the blue ones. We start increasing the value of scale each time, seeing some graph connections between the red dots and the blue dots. And now that we have the graph connections, we can start calculating the persistent diagrams and calculate the number of cycles in each scale. Now, if we measure barcodes, basically lifetimes of various cycles in various dimensions, we will see that the maximal lifetime, and you can prove that in theory, is bounded from above by the Hausdorff distance between P and Q. Why does that matter? If this characteristic is, in practice, big, this means that these manifolds are in fact dissimilar. And based on that knowledge, we can determine the measure of similarity between the manifolds. It doesn't have to be about images. We take the wholes of dimensionality 1 and we calculate the sum of barcodes, the so-called cross barcodes, the barcodes for space vector. Let's talk about this complex mathematical concept, but how can it be applied in practice? a mock example. We have some artificial data, a combination of Gauss distributions, 5 components, and using this data, we can train a commodity gun with all the 5 components, or an advanced gun, W gun GP. For some reason, it breaks down, it loses in distribution modes. What we expected is that with the data that match the commodity gun, the measure of proximity should be almost 0, because we generated artificial data very close to real data. As for the W-GAN GP, it should be the other way around. When topological attributes are calculated separately, and we simply evaluate the L2 range between them, we do not observe what we wanted. In both cases, the measure of similarity is the same. This is counterintuitive, and if we use my approach, the one I described, it works beautifully. So this measure is very sensitive to these basic things, and we have conducted a detailed research of how it works, how it is applied in practice, and now let's review this very important example, the evaluation of gun quality, gun performance with images. There is the standard metric, which is widely used, commonplace in research. FID. We took this recent data set, FFHQ, a big data set of high-resolution images. And so we used this data set to first train various generative models based on guns, and we calculated the FID parameter. The models had different architecture, different capacity, and so as the architecture changed, the freshened, the FID parameter improves. We ran the same experiment with the artificial measure, so the x-axis is the FID and the y-axis is the measure of similarity. And so we see that between the two, the correlation is almost perfect. This means that this measure of similarity can be used very well for images because it has all the attributes that people are accustomed to. Because once again, FID is used widely, as I said. Also, this metric can work not just for images, but for random arbitrary objects, time series, for example. It can be differentiated, and it can be calculated very, very quickly. The flicker faces, the flicker manifold, the dimensionality of the image is 10 to the power of 7 or something. So, despite that, still, the calculation of the metric is done very quickly, and the metric is subject to differentiation. So, one of the conclusions is that machine learning is clearly science about data, but primarily about the form of data. If you know the form of data, if you can characterize it in a certain way, you can learn a lot about the properties of these data, about correct predictions, and how you can factor in those properties in building your prediction model. In my presentation, in my work, I have been building upon the form of data with the adversarial attacks. It's very important to, for example, take into consideration where the data live. You can also use subtle topological characteristics to assess attributes of sequential data. This is where you can figure out if they are adversarial or not. And using geometry and topology, you can compare complex manifolds with complex structures. In my opinion, this area of work, combining geometry, topology, deep learning, machine learning, I think this holds a lot of promise, and it is ripe with new breakthroughs. Thank you very much. Thank you, Evgeny. You personally, what do you think is your biggest achievements in artificial intelligence? That's an interesting question. You know, I've never really thought about it. I'd say that there are certain things, certain applied applications that I'm proud of, the things that my team and I have been working on, implemented in engineering centers in Russia and abroad. Airbus, for example, use our solution, and it's no wonder when we were developing these algorithms, we managed to introduce new, say, knowledge, new properties to them. As for the recent accomplishments, just a few years ago, together with one of my postgraduates, we published a widely quoted paper on graphs and representation of graph data.
Could you please answer this question? Many scientists think that a human brain has a quantum nature, and you cannot build the similar machine. What do you think about that? I don't like philosophy, really. I like to focus on engineering tasks and engineering challenges. You know, the big ones. They inspire and drive the fundamental science as well, because there is a need to develop very complicated concepts. The modeling of the human mind is very important, and the very important challenge. But looking at it from the perspective of quantum computing, well, I don't know. Maybe someone will invent something else and it will work. And maybe it won't be a quantum thing. But let's take Skoltech. What are the priority technologies there? Well, you know, Skoltech has just received a grant to develop the research centers for AI, and I am heading one of them. And we are talking about the development of the AI methods to resolve the sustainable development tasks. We're talking about ESG risks, and here you need to monitor the carbon balance of some regions. You have to estimate their impact on the economy. This is a very important layer of tasks where you need to process the data of the remote sensors, and you need like a physical. This is a combination of the physical modeling and the machine learning, because we're talking here about the scientific processes, obviously, because, you know, like the pollution and other things and its propagation. And these are very important, daunting tasks, and ML is the future here. No one can resolve that. Thank you very much. Thank you very much for such an exciting presentation, and we are looking forward to seeing you at the next conference. Thank you.